Today I'll be talking about Git, and Git is a revision control system that I've been using for quite some time to tracking the Linux tree. We'll talk about a little bit more about the Git history in the second section. So first we'll talk about the concepts. If you haven't used SCM, this might be a little bit of a background info for you. We'll talk about the repository structure, and the majority of the talk, about the last 45 minutes or so, will be spent on some basic commands that are useful when you're using Git. So let's start with the concepts. So this particular section is not really Git specific. I'm trying to use some wording from Git terminology, but the majority is just about tracking your code in a source control management system. So we want to track changes. We have a repository and a working directory. The repository is the database of all of our changes. The working directory is what you edit, your code, your documentation, whatever that happens to be. So we have two kinds of SCMs. We have a centralized SCM, like Subversion and CVS, where you have a single server, and the clients are communicating with the server to get all of the metadata about about your repository, and then we have a working directory on the client and the current state. And decentralized, we're removing the server. Anybody can become a server, and they can share the repository. Everybody has the complete history of the project, and it's obviously decentralized, so we can disconnect ourselves from the network and work on a train. So components. So we have a working tree, and if you're not using an SCM, you already have a working tree. You have a bunch of directories and some files where you keep your code. And in the repository, no matter what SCM you're using, you will have some kind of a representation of files. Multiple files or multiple states of files will be grouped together into a commit. The commit will have some information about who made this particular change to the files, when that occurred, and a message describing the changes. So sometimes in some SCMs, this commit will contain deltas between this revision and the previous one. In Git, we're actually storing complete states. We have ancestry. Every commit has a parent pointer to the previous commit that came before it. And in good SCMs, we have parent information about as many commits that influence that particular commit. So SVN is not one of those. It's difficult to determine where the commit came from because there is no ancestry information. This ancestry forms a, that's not the correct term. Anyways, the acronym is DAG. I don't remember the third word in it. And this represents the history of, does anybody remember? Acyclic. It represents the history of the project. In this particular example, our commit A is the oldest ancestor. There was a branch into two commits B and C, and then there was a merge in commit D, and so on. So most SCMs will have tags. A tag is a name you give to a particular commit in history, and a name that you want that particular commit to be represented by. This is very frequently used to tag things with the release number. So here we have two releases, 1.44 and 1.5.0, and those were particular releases of this particular project. So tags do not, while revision control systems or SCMs allow you to move these tags, usually the way you use tags is you assign it to a commit, and it's forever pointing to that commit. We have branches. The way the branches differ from tags is that branches actually follow a path of development. So if we have a particular branch and we make a commit, let's say on top of commit H, this topic branch will actually advance, and it will now point to the next commit. In Git, there's a concept of a head. A head is a pointer to a branch most of the time, and this identifies the current commit that's checked out in your working tree. So when we have a head pointer to topic A, that means that the commit H was checked out into the working tree. So if you haven't modified any of those files represent commit H, or the state that commit H was committed with. Sometimes, however, the head can be detached, and I actually will not talk about this in this presentation because that's a more advanced topic. But if there are any conflicts in certain Git operations, Git will detach the head and it will point it to a commit that it's currently forming, and the topic will, the branch itself will be pointing somewhere else. And last concept is some kind of a staging area. All revision control systems, or SCMs, have to maintain a list of edits that you want to commit on your next commit that you'll be making. So, for example, in Subversion or Git or Mercurial, you have to tell the system to add a file to be tracked. So you're going to be issuing a Git Add command that has to be staged somewhere, and the index is the part of the SCM that maintains that information. So what's to be committed? And that's it for components, and now we're going to move on to operations. So there are several general SCM operations that any SCM will have. So the first section are things like initializing the repository, so we're creating a new database to store revision information in. Checkout, which means getting things out of the database into the working copy. Switching between branches. Then there are things that allow us to stage commits, stage files to be committed, like adding, deleting, and renaming files, and then creating the commits. Then there's the data mining component, where you can get status, which is usually the state of the working copy with comparison to the last commit that was checked out. So this will tell you which files you've modified on disk that have diverted from what's at the head commit, or the head. Diff will show you the differences, so it will look like a patch output. And log gives you the historical look at what changes were made to the revision of the project. Then we have reference commands, which create and manage tags and branches. So a centralized view. On the left-hand side, we have a server, and on the right-hand side, we have 3 clients. And they all can do checkout, update, diff, log, and so on operations when communicating with the server. But there is a distinction here because the left-hand side has our DAG, our repository, and the clients do not maintain that information. They only have the checked out files and directories and folders. So we need a server. That's our single point of failure. If that machine is offline, then people can't make new commits. And it's the bottleneck. Certain operations have to be serialized and could be slow because of network lag and whatever. So decentralized systems add 3 more operations. You can clone, which is a complete replica of the server or the repository's information. You can pull, or some systems call it a fetch, which gets the information from the remote repository and brings it to us. And you can push, which is the opposite. So it takes all the information in the local repository and updates the remote.
How would clone and pull be different?
So clone initializes a new, there's a question about how clone and pull differ. Clone initializes a brand new repository, which pull does not do. So pull brings any recent information from the remote that you don't already have, whereas the clone initializes a local repository and it must bring all the information because there's nothing here yet. But they're fairly similar. I think Git optimizes the clone slightly because it knows that you're getting everything. So this is the view of what decentralized systems look like. Basically, every system here could be a server. You can't really identify which one is the server because they all have the repository, and they all can have checked out working copies, and they can all clone from each other. They can all pull and push between each other. There's basically no functional distinction. Everybody's running the same software. There is no server software versus client software. So a little bit more about decentralization. So in this example, we have some public repository that's managing a project. We are going to clone to our local machine and create our very own repository, which is a complete duplicate of what's on the server. We can make local clones of that repository, which are very lightweight with Git. There's almost zero overhead. It's like 64K or something like that. It basically has to reproduce the references, so the branch pointers and the tags. But if you tell it to, it can use hard linking or other methods to leave the actual repository information, the bulk of the history, inside the pristine copy that I've called it here. These are just named for illustration purposes, but you can call them whatever you want, and you can build your own workflows however you want to work. So once we've done some changes in these repositories, we can push them all the way back to upstream, or if we don't have commit or push privileges to upstream, we can create our own server and tell the world to grab our changes to the project from this other server. If you have another machine, you can clone that repository to another trusted peer and do cross-development, pushing between those two repositories. They can both push to a web server. It's fairly flexible. So this is what distributed SCMs let you do. So is it any good? So the four things that I like about distributing the SCM is you can do what I call non-intrusive micro-commits. So anybody can commit as often as they want, and it doesn't have to break the build because you don't have to push your changes to the server. So you can commit every hour, every 15 minutes, every day, whatever you're comfortable with, and when you finish the feature, that's when you push it to the server. That's when you share it with the rest of the development team. So you can fix any of the mistakes you've made while still committing fairly frequently. Now, the reason why frequent commits are fairly important is if you remove some code or if you do a major redesign of the code and you've modified a lot of it, and at a certain point you want to go back to an intermediate state, if you're afraid of breaking the product for everybody else that's communicating with your subversion tree, then you may not want to commit fairly frequently. And then you've lost all that history between when you started the major change and when you're finished. And sure, most SCMs allow you to create private branches on the server, but then if you have many developers, that creates a big name creep where you have lots and lots of naming conventions, people putting their names on branches, and you can end up having a very long listing of branches on the server, which is fairly frequent in CVS and I guess Subversion too. Detached operation, these are things like working on a train, but also there are things like the server's down and you still want to make a commit. Well, you can do it on your own laptop and then push it to the server, or even share your work with the guy in the next cubicle just over the network without involving the server. So there is no single point of failure because everybody can be a server, and everybody has a backup. So there's no worries about the data being lost. Anybody that's done a pull or a clone from the server has the complete history. So here's a little bit of history on Git itself. In 2002, or prior to 2002, the Linux kernel was not being tracked officially by any system. People were using Subversion or CVS to do their own private work, but there was no sharing because there was no system that was capable of handling the load, the amount of code that the Linux kernel creates. BitKeeper came along, and Larry McVoy offered BitKeeper licenses for free for Linux developers to use, and I guess for any open source development. And Linux became the first big user of this particular license, and it improved BitKeeper a lot because BitKeeper was forced to fix the bugs that people were finding now that they were using it in such a big project, and also the Linux development started scaling a lot better. So everybody was happy. Unfortunately, in 2005, after a strange turn of events, Bitmover withdrew the license that allowed Linux developers to use Bitkeeper. And Linus started searching for an alternative. So he went across the landscape and tried every revision control system he could find. And he didn't like any of them, mostly because they couldn't scale. So he started writing his own. And 2 weeks later, Git was self-hosting, so it was being developed in Git, and it could merge branches. A couple of months later, it was the official system for tracking the kernel. And 2 years later, 1.5 was released. And I think 1.5 is the first good release of Git. Prior to that, the system was very usable for people that were following the development of Git. It had many really good features. It was really fast. It was scalable, but it was very difficult to get into. So you would be forced to swear for 2 months until you got it. And once you figured out how it works, then you could use it productively. In the 1.5 cycle, I think there must have been a big pressure for fixing many usability issues. So this was the time when many kernel developers started complaining that the newcomers to Git, started complaining, like for example Ted So, about the usability of certain commands, and because of the big push, documentation improved and the usability of the tool improved.
How big is the Linux kernel? Like, why was scalability such an issue?
The scalability of the Linux kernel is not because the Linux kernel is so big, but because of the amount of changes. So I did a talk a couple of weeks ago on the kernel, kind of an overview of the code, and I don't remember the numbers, but we're talking about thousands of lines being changed per day, and we're talking about hundreds of merges per day. So we have 1,000 developers developing, and they're all making small commits or large commits, whatever they happen to like to do, and this has to all be merged together. So if you can imagine the amount of merging that happens, SVN just doesn't cut it. Subversion is horrible at merging. If you ever diverge your development in Subversion, merge it, and then try to merge it subsequently, you will find that you're resolving the conflicts from the first merge again. Right, because there's no parental information, there's no parental history being kept from commit to commit. So Linux kernel, I think, is like 300 megs or so, and about half of it is in drivers, and there are drivers being added every day, and it's a big piece of code, and it's not that it's static and it's big, it's that it's very dynamic. I don't know, maybe every year 20% of it is completely rewritten. So.
And how far back do the deltas go now? Do they go back to the start of Git, or do they go back farther than that?
There are multiple trees, but the official tree starts at 2.6.12, which is when Git started tracking the Linux kernel. So it's the.
So they couldn't convert from Bitkeeper? They just.
Somebody did eventually, but they didn't have those tools when it became the official tool for tracking Linux kernel. And what would happen if they merged the historical tree and the new tree together, it would convert all of the references, like in Subversion you have numbers, right, commit numbers. So imagine all the commit numbers changing for the new tree by bringing it over. So you can do it yourself on your machine, and you could continue developing, but you wouldn't be able to easily merge those changes together. So one thing I'm not covering here, but it's kind of related to the question, is Git is using SHA-1 sums, which I'll talk about a little bit later, for creating the IDs of the individual commits, and that makes it cryptographically secure. And if you get a SHA-1 and you compare it with somebody else's SHA-1 that supposedly has the same tree, they should be identical. You should be able to compare those two IDs and be able to, within certain certainty, say that you have the same tree just by comparing the SHA-1. So if you had this other tree and you merged it in underneath, it would basically ripple all the way up to the top and change the top commit. So then you would basically have two incompatible trees that you would no longer be able to compare to each other. But however, KDE, for example, KDE is in the process, I think, of converting Git, or at least they're thinking about it. Because in Subversion, I think their entire project was 300 gigs, and under Git it was 30, or within that order of magnitude. So they were pretty happy to be able to. Gigs.
Is that because they were putting a lot of images in? Like...
Because KDE is huge. And I imagine some of it are PNGs before they started using SVGs for icons. I'm not sure about that, but Git's just more efficient on the back end for storing the data. And they needed some features, and I think some of those features are being developed. I can talk about that after when we finish all this, all the presentation, and maybe we have a little bit more terminology, so I can back on that. So that's all about the history that I wanted to say, and the next I'm going to talk about the repository structure and an overview. I'm not going to get very deep into it, but I think that some of the ideas in this section are very important for understanding what happens later on in Git, because it's different than what you're used to. So the structure. So we have a repository. This contains the metadata, the history of the project. We have an index, which is the staging area that I've mentioned before, and this contains the information about what you want to commit in your next commit. And we have a working tree. So this is the files that you have on the disk that you can actually tangibly see. And the operation that allows you to take files from the working tree and adding it to the index is called staging, and then you'll be executing commands like add, remove, and rename. And committing, that creates commits into the tree, so it creates new commit objects within the DAG, and it advances the branches appropriately to point to the new commit. Then we have the reverse of that, which is reading a tree, and here are some operations like checkout, read tree, and reset that perform this task. Then we have checking out, which are taking files from the index and updating the working tree. So we have, again, operations like checkout, checkout index, and reset. Some of these operations you actually won't be using. Checkout you will. So this is what the repository looks like. There's a single .git directory inside your project. So with SVN, you had a directory for every, so you had a SVN directory for every subdirectory in your project. Here there's only single .git directory at the top level of your project, and it contains a bunch of files that aren't particularly important, but a few are. So inside .git there's a config file, which is the per repository configuration file where you can set certain parameters, and we'll look at a few of those later. There's a description which just describes in English or whatever language you want, describes the project, and I think it's only used by GitWeb. This is like CVS Web. Allows you to view the repositories through your web browser. Git Info Exclude is one way that you can tell Git about patterns that you want to ignore. So for example, I'm a C programmer, so I often ignore .o files because I don't want to include them in the repository. And next we have objects. So inside .git we have an objects directory, and we have a bunch of files in there. So we have two kinds of objects. We have loose objects, which are loose because there are many of them, and then we have packs when we take loose objects and we combine them into one file for performance reasons, for quicker access. We get pack files, and the pack files are gzipped and they contain deltas inside, and not particularly familiar with the most current pack format, but they also come with an index which just makes accessing the pack faster. And this is what an object looks like. An object has a type, a size, and some data. It's content addressable, and what that means that we take the whole blob of the object, we're going to take the SHA-1 of it, and that's going to generate a very long hexadecimal string, which is going to be the unique identifier for this particular object. Then we can take that key, look it up in our data store, and we can get that object back. So it's content addressable because from the content we've generated the key that allows us to address that particular object. The four basic types. The first one is blob, which represents a file in your file system at a particular point in time. We have trees. So tree objects are like directory entries or indexes. They contain SHA-1 sums and the file names and the modes of files that they point to. So in this particular case, that pointer, the first one, points to a tree. So it points to another object, and it's addressable by the SHA-1 sum within the tree object. But they can also point to blobs. And any leaf in this tree is a file because Git doesn't care about empty directories. So if you particularly are worried about empty directories, you would have to drop a file in and store it in your revision control system. It could be an empty file. We have commits. Commits point to trees, and they will have information about who made the commit, who was the author, and who was the committer. And those are two different entities for a reason, which we'll talk about a little bit later. They have a tree address, which then points to the top level tree, and then it ripples down to the blobs at the leaves. And the commits will point to other commits through a parent pointer, and they'll create a linked list or your DAG, your tree of commits. So you can have one or more parents, and actually the first commit will have no parents because it's the first commit. So then we have tags. So a tag object is similar to a commit, but nothing points to it. It's just basically an object that describes both through a name and through a commit message, a tag message, what the tag is representing. And actually tags, I don't think, have to point to commits. They can also point to trees. So if you want to tag a particular subdirectory within your project, I think you can tag that as well. Objects are immutable. They cannot be modified, but they can be deleted and replaced with a slightly different object that represents similar data. So in this case, we have data prime because I've modified this particular file or directory or whatever. And I've replaced the original object. But that, of course, means that the content has changed, so now we have a new SHA-1 sum. So the old SHA-1 sum would represent the content of the first object that we've deleted, and it can no longer be accessed. And the new SHA-1 sum will access the new object that we've just created. And now we're going to get into the bulk of the presentation on using Git. So I'll start about talking about the structure of commands. So like in CVS and Subversion, we start off with a Git word, and then we specify some global options, and then we're going to specify a command, and finally we'll have some command options. So, oh my God, there are 137 commands. So the first complaint that people have when they come to Git is when they type in Git space and they tab, they get all that, and they don't know where to start. So actually, for everyday use, you only need about 20 commands, so you don't have to worry about the rest. Then there are some GUI commands that might become useful, and I'll show you a couple of them. I can't say that I use them very often. Git K is probably the one I use the most often. And then once you get more familiar, you might bring in another 20 or so commands, and the rest of it is called plumbing. The way that Git was originally developed is it was written by with a bunch of shell scripts. And those shell scripts talk to a few C programs that were just fast for the reason that they needed to be fast to make the rest of the system fast. And as the system progressed, more and more of the shell scripts became C programs as people decided that they were important enough and frequently enough used that they should perform well. So certain commands took a little bit longer to get converted into C programs because they just didn't need to be. And C, just by the virtue of this kind of development, Git was very scriptable because it needed to be. There were lots of little programs that were scripted together to build higher level constructs. So usually the porcelain layer, the layer that you would interface with, which is in green and blue and a little bit of the brown ones, would be the commands that are porcelain. And initially they were shell scripts, and they would call the plumbing, the gray commands, to execute all the low-level things. So you can get a list of the common commands. This is, I think, about a dozen or so, maybe 20, just by running Git Help. This gives you like the entry to the help system. Any command will answer the -h flag, and it will give you the syntax or a short description of what the command does. The verbosity of this output will vary. And if you want more information, there are, 137 or more manual pages, and they are very detailed as of the 1.5 release cycle. And they give examples at the very bottom and why things were designed the way they were, and there's lots of information. So you can invoke man page viewer either by running man and then giving it the git dash command, or you can say git help and specify the command, or you can say git the command and dash dash help. So if you want to start, you can say git help git, and it will give you the introductory page that starts you off on in the manual. So besides having a per repository configuration file, I think there's one that you can drop in /etc, and also you can have one in your home directory. So this is .git config, and the interface to the config could be either through an editor or through the git config command. So the git config command will, with the -- global flag, will allow you to modify the global configuration file. By default, it communicates or it modifies and reads from the per repository configuration, file. So here's an example of how to set your username and email and some UI preferences. So this is what my git config file looks like. I think there are a few more lines, but that's the summary. So one requirement is that you set your name and your email. And the reason why Git needs that is this is what goes into the commit history. So every commit will have your name and your email address because you're the author of that commit. So if you want to create signed tags, so you can use PGP crypto to sign your tags for more security and identification. You can specify your key. I think it uses a default one that PGP will define in its configuration anyways. And there are some other options. Two features that I like is to use a pager for the output, and the FRSX, I don't know what they all stand for, but basically it makes less not display the pager if your output is shorter than what can fit on the screen. So if your terminal happens to be 20 lines high, then if you have 19 lines of output, it will not present the pager. The other one is to show color highlighting in the output, and that's the color UI auto setting. So if you're piping the output into a file, it will not color it, but if you're on a terminal, it will. So we'll see a little bit of that later. So we're going to go through the process of creating our first commit. So we're going to start by creating a new repository. So we don't have a remote that we're going to talk to yet. We're going to create a brand new project on our local hard drive on the laptop. The command that we're going to use is git init. It's ran inside your project workspace, and it just creates the .git directory. And now, what to commit for our first commit? So we need to stage some files. So you can either say git add file, and then specify as many files as you want, or use asterisks to glob files. Or you can do git add dot, which recursively ripples through the tree and adds everything that's not in the exclude patterns. There's a question.
I was wondering what the difference between the excludes file of the repository and .git.
I think I mentioned it later, but I'll answer the question now. The question was, what's the difference between the Git Info Exclude and .git ignore? And the difference is that nothing inside the .git directory is tracked. So you can't add the Git Info Exclude file into your repository, but the .git ignore you can. So any personal preferences you have, you would put into .git Info Exclude, and anything that you want everybody else on the project to ignore, you would put in the .git ignore file. So removing files, git rm file. You can rename files using git move old new. Here's the example of that I think is in the man page for a default .git ignore. So again, this you can track. And to create a commit, use the git commit command, and without the -a modifier, it will only commit what's currently in the index. So anything you've staged with the rm add and move commands will be added to the new commit. And if you specify -a, it will commit everything that has been modified that Git was already tracking. So it will not pick up any new files that were created, and it will not pick up any files that you've removed but you didn't tell Git about removing them yet. So basically, if you edit a file and you do it git commit -a, it will pick it up. So we're going to go through a visual example of what's actually happening. So there's a disclaimer here we're using white pixels that I'm not showing what the index is actually holding. So the index is going to show us what objects will be added to the repository once we actually make a commit, but I'm not showing the internal index representation, which is slightly different. But you can think about the index looking the way I'll be showing it in this diagram. So to proceed, we're going to make a project directory. We're going to enter it, and we're going to run git init. So this creates the .git directory on the file system that's below the dashed line. Then we're going to create our first file, a very interesting file, contains test. And again, there's nothing in the repository yet. There's no changes there. There's just a file in the file system. We're going to do a Git Add Test, and this tells Git that we want to stage this file. So now the index is going to start tracking our test file. So it created a tree object with a SHA-1 which actually is much longer than what we could fit in the box. And it created a blob. So the blob contains the, again, the blob word, the length of the object, and the content of the test file, which in this case happens to be test. The tree node represents the directory that it's pointing to. So it's going to have a pointer to our 9DAEFB object, and it's going to have the string test in it because that's the name of the file. And then we're going to commit it. So the commit command is going to create a commit object with its own SHA-1, and it's going to point to the tree object that we already know is going to come because it was in the index. And there's the output of the commit command, which basically tells you how many files were added and how many insertions of lines and how many deletions of lines, and it identifies the new commit ID. The next command we're going to run is we're going to create another directory which we want to track and put a file inside it. So here the interesting part is that Git is actually going to reuse the initial blob because it hasn't changed. The only file that we modified in this step is we created a new file under the directory dir, and we've added it to the repository. So the top tree is the representation, the top yellow tree is the representation of dot, our current working tree, and then we have two nodes under that, which is the test file and the dir directory. So we have a tree object for the dir directory, and the test file has its own blob, and then the foo file has its own blob. And once we commit this, we have a new commit object, which points to the new tree, but the old commit object still points to the old tree. So the index is pointing to all the yellow objects, and we can reference all the objects by following the pointers. There is a pointer from the commit pointing to its parent, the original commit, and this is our DAG. So it's non-cyclic, which is one of the requirements for it being a DAG, because there are no cycles here. Arrows only point in one way. And if we want to get the files from the first commit, we follow the pointers all the way down, and we only find one file in one directory. And if we want to get the files from the second commit, the 5.2 commit, then we follow it to the top level tree. We notice that in that tree there is one file and one subdirectory. We follow that link down, and we find that the second directory only has one file inside of it. Any questions?
I like the colors on your screen much better than the ones on the wall.
Yeah, so people that are watching the screencast will actually see the colors. The presentation on the wall has slightly different colors. All right, so this is the building block that we're going to follow. So another thing that you should note is that the master branch has followed to the new commit. So creating the new commit has updated what the master branch has pointed to the new commit, which makes sense. You're working on the master branch, and you make a commit. You're still on the master branch, and the parent of that commit is the subsequent commit. So if you want to see the history of the master branch, the command that views the history will show you the commits within that chain. I have a question.
Where are the file permissions stored? Are they stored in the blob?
Just like inside any file system, the permissions and the file names are stored inside the directory entry, right? So in this case, the tree object, which has no name because it is the root of our project, it doesn't have a name for itself, right? But it has the name for the test object that's beneath it, that's the file, and it has a pointer to the dir object, which is the subdirectory. Okay. So inspection. So here is where we're going to look at the state of what's in the repository. So the first command is git status. So as I mentioned before, this shows what's changed between the what we have checked out and what's actually in our file system. So it's going to tell us about the staged changes, so things that we've added to the index. So if I tell git add file foo, it's going to add that to the index, and it's going to show me in the list of staged files. It's also going to show me unstaged changes. So if I edit a file and I haven't told Git to start tracking this new state, if I run git status, it's going to show me that as an unstaged change. And there are also untracked changes, and these are files that are not in the exclude file, they're not in the ignore file, but they are new on the file system. So before I initialize my .git ignore file, I will have a lot of untracked files if I have an active project. Diffs. This is a way to check, just running git diff will show you the differences between what's in the index currently, so it hasn't been staged yet, and what's in the working tree. So if I modify a file and I run git diff immediately after, I will see the change in git diff. It creates patches. It's like the diff command, except for it's implicitly checking against the index. If you want to check the differences between the commit and the index, so basically what was checked out and what has been staged, then you run the git diff -- staged command, and it shows you the differences between, again, what's in the repository and what's been staged into the index. Git diff head checks the changes that you have on your file system with respect to what's on the commit that was checked out. So these are the three different combinations of comparing different things. And the next form is git diff, and you specify two different commits. So let's say I want to find out the differences between two tags. So I can tell it, give me the changes between version 1 and version 2, and it's going to give me a patch between those two revisions. I have a question.
Can you put a branch name or head?
Yes. So what are these commit IDs that I can specify to git diff? You can specify the full hash, the full SHA-1, if you want to paste it from somewhere, for example, you probably won't be typing it in, or you can abbreviate it. Git will actually take any form of abbreviation as long as you want, as long as it's unique. So if it's not unique, it will complain that it's not unique. Otherwise, it will use that. You can specify a tag. So here it's in blue. We have a tag that was created previously. We want to use that as an ID for git diff. We can do that. We can specify a branch, a local one, or a remote one. We'll talk about remote branches later. We can search by commit. So : is a special syntax that we can use for searching a pattern within the commit. So if you know that your commit started with foo or some text, you can just specify that, and it will resolve that into a commit ID. And here I don't think it's actually a unique match. I think it's the first match. Then we have a bunch of other magic names like head, fetch head, org head, and merge head, and other things, which I won't cover, but they're magic words for specifying different kinds of commits. So if you're in the process of a merge and there was a conflict, there's a special tag to tell you what the other branch was that you were merging in, if you want to use it in a script to automatically resolve like PDF merges or something. So you can also augment any of the nouns that I've mentioned on the last page. So any of the things I've mentioned before, like the full SHA-1, the abbreviated SHA-1, you can append to that a caret or a tilde1, which means one commit before that within the commit tree, within the DAG. You can use 3 of them, or tilde3 to specify 3 back. And of course, you can substitute the head with any other commit identifier to make it go 3 back from there. You can say branch at yesterday, which means what did my branch look like yesterday? And if you don't specify the at, it just means that you want to implicitly use head. You can specify dates, so if you want to see what the branch looked like on June 1st, you can do that. You can, of course, specify a year if you want to go further back. You can use cardinal values for that, so you can say, what did my master branch look like 3 changes ago, and it will find that out for you. So another way of looking at changes is to use the git show command. If you run git show by itself, it just shows you the last commit. So this particular representation is what commits look like when you ask Git to show you a commit. Commit will always have and these are the colors that will show up on the terminal when you run git show and you have the UI thing enabled in your Git config. So it will show you the full shell one, it will tell you the author, it will tell you the committer if it's different than the author, and there's a distinction there. It will show you the date of when it was created and a short description of what the commit is. Then it will show you the patch. So for every file, it will show you hunks, and in every hunk, it will show you lines that were added or removed. By default, it uses unified diffs, but I think if you prefer the other format, you can change it. So there's a short form to show less information. If we just have one file and we modified one line, git show fits on one screen. And if we're just trying to get a glossy overview of what changed, then that's it may be too much to view 100 different files. So Git Show Stats is the diffstat output. There's a Unix utility called diffstat that basically generates this. Git goes one step further, and it colorizes the pluses and minuses in green and red if you have the UI option enabled. So that's the output of that. And it also gives you a short summary of how many files were changed and how many lines were inserted and deleted. There is a name status, which gives you an SVN-like output, so A for added, D for deleted, and M for modified. You can also show any particular revision, right? So you can look at a head commit, 3 back from head, 10 back from master, or what master looked like on my birthday. There is also a special form that Git Show will use to display the contents of a file. So if I specify any particular revision ID and a file name on that revision ID, it will dump out the contents of that file with a colon in between. Logs. So logs will show you the history. So no matter what branch we're on right now, Git log will start at the current commit, and from the most recent to the oldest, it will show you all of the commits. If you have the pager enabled, it will present that in less if that's your default pager, and then you can scroll through it and search through it and so on. So Git log is actually a very nice way to drill down the history and find changes. Just because Git allows you to filter what comes out of Git log and similar tools. So we can specify arbitrary ranges. So by default, when you specify a revision, Git will start from that revision, Git log. Implicitly, it will start from head because that's the current checkout commit. It will start from head, and it will display all of the revisions like we've seen here. So head is implicit here. But if we specify another revision, it will start from there, and it will go from the most recent, which is the one we've specified, and it will follow all the parents until it gets to the end. We can, however, specify a range going between a tag and a branch or any other two IDs. We can specify a head or a commit with ... afterwards, which means the opposite of the default behavior, which is start from this commit and go all the way up to head. So again, we haven't specified anything after ... so head is implicit. So it will basically display the last 10 commands. And the fourth line there, -10, actually does something very similar. It means start from head and display the most recent 10 commits. It limits the display to 10 commits. The third form is pretty neat, and it allows you to show everything on one branch and everything on the other branch, but nothing that's common because we've specified a common point. So if we know that the branch diverted a particular commit, or maybe even we know that it diverted since a particular commit, we can specify a common point, and that's the stop when Git will stop displaying commits. So it's going to follow everything on branch 1, everything on branch 2, and it will stop at the common point. So you can also specify the range using two dates like the last form. We can also not limit it by a linear range, but we can filter out certain commits. Like in this case, we only are interested in commits that were authored by Fred. So we're going to say author equals Fred, and it's only going to show us those commits that, that Fred made. Again, starting from head and working all the way down to the beginning of the project. We can search by committer, or we can grep through the commit string. We can also grep through the actual changes. So we know that somebody changed function foo. We can say git log -S foo, and it's going to show us all of the commits that made that particular change, that had foo in the line that was modified. And you can use regex also to search. This feature is called pickaxe. So git log also allows you to specify a filter to show you only commits that modified certain files. So in this form, we're going to show only those commits that modified a particular file. Grep, Git has its own built-in grep, and it's, I think, about 10% faster than grep talking to the file system. Because of those packed files that we saw previously, they're very efficient. And the reason why they're efficient is when you need to scan the whole file system, it usually involves a find Unix command and a grep Unix command. And it means that the commands need to open every single directory inode, and they need to scan that inode for subdirectories and files. They need to open that file, they need to read in that file or memmap it, and read through all of it. Whereas with packed files, Git only has to load one file into memory as a single operation. It does need to decompress it, but that actually happens because the packed files are compressed, but that actually happens to be a faster way of doing things than talking to the kernel for every single file and for every single directory inode. Yes?
Do you create pack files manually, or is it do it automatically?
I will talk about that later on. Pack files are created manually and automatically. In this particular instance, we're we're specifying a branch, right? So not only can you search the current checkout for a particular pattern, but we can specify any ID, any commit ID, and it will search within that. So branching, a very, very important part of Git workflow is branching and merging. It's distributed, so you'll be often merging. You're merging just by the virtue of somebody else checking out your project, making a commit, pushing it to the project, and while you're doing your work, the repository upstream has changed. You've made some commits. So when you pull from the repository and you get changes from the other person, you will have to merge them with your local commit, with your local changes. So references. References are things like branches and tags that basically point to commits. They're very lightweight. You can alter them at any point. You can throw them away, and we have three basic types. So we already talked about branches. Git branch -L shows you all of the local branches, and they live in the .git directory under that location. We have tags. Git tag -L displays all the tags, and they live similarly like branches under Git refs. We have remote branches. So we'll talk about that in a few sections, but remote branches are ones that are tracking remote servers. So we can get the changes from a remote server without actually merging them into our project. Particularly if the remote has multiple branches, it doesn't make sense for us to merge all of those branches like experimental and testing and my fancy feature A, my fancy feature B all into our working tree because they may not be finished. So there will be branches which will not be merged into your project. And this is called multi-headed revision control system because it's able to hold multiple heads within one revision. Systems like Mercurial, I don't know what the status is currently, but when I was using Mercurial a few years ago, there was no way for a repository to track multiple heads. It would only have the head that was checked out. And when you pull the repository into your system, you would actually have to merge it. So again, these remote references live under Git refs just like the other ones. The way we create a branch is with the git branch command. We specify a name for the branch that we're creating, and we optionally can specify a commit that we want that branch to point to. So recall our graph, the branch points to a commit. So here we can specify a different commit than the implicit head that it would use otherwise. Git checkout that, with a name will switch to a different branch. So if we're on branch master and we want to switch to another branch, we specify the name. You switch to local branches. You usually don't check out remote branches directly. The -F will force an overwrite of modified files that you have on your local disk. You can do 2 operations of creating a branch and switching to it with one command. Git checkout -B does that for you. So with the -B, you can specify the name of the branch you want to create, and by default, it will use head, but if you specify a different commit, it's going to use that commit, create the branch, and check it out, so switch to it. So if you do have local changes and you run git checkout name to switch to another branch, Git will complain that there's a file that was modified that hasn't been committed yet. And one of the things you can do is you can specify the -M flag to git checkout, and this is going to merge the changes that you have in your working tree onto the new branch that you're switching to. So if you have a small edit and you actually started working on the wrong branch, you can switch to a new branch. You can, of course, switch to a new branch. You can create a new branch with -B and switch to it, and it will take all those changes, create a diff for it behind the scenes, and apply it onto the new checked out tree. So we're going to do a little example of what happens when we're working on branches. So we're going to start with a fairly new tree with one commit and a master branch pointing to it. By the way, I stopped using the head reference here, so if you see a dark green branch, it means it's been checked out. So that's the one that head points to. So that's our current branch. So master is a current branch. It's pointing to commit A. We're going to do a git checkout -B to create a new branch because we want to work on a bug fix. A common workflow is to create branches for a particular task. So if you're working on a new topic, you can create a new branch for it. You can always work on master if you want. That's the default branch you get when you create a new repository. But a common workflow is just to create a new one because you never know when you're interrupted and you need to work on something else. So let's start a bug fix branch. We're going to be fixing a particular bug. We're going to do a commit. Oh, I do have a head pointer. Okay, so we do a commit, we do another commit. The bug is not quite finished yet, but you have some idea that you want to implement, so we're going to create a new branch. So here we're going to create a branch off the side, and we're going to do some commits there. So I've created commits D and E, and obviously the project has diverted. We're now on this other branch, and we think we're getting somewhere, so we tag it. So we're happy with this particular state of the project. So here we can see that Git Tag takes a couple of parameters. We can define a short description of what the tag is along with the tag name, and then later on when we're inspecting the tree, we can see that the tag has a description. So then the manager comes along and he asks about the bug, so we have to switch back and fix it. So we actually finished our development on this particular bug. But we want to keep going on this other feature, so we switch back with git checkout, and we make another commit. So now we finished this feature, we know that the bug is done, and we want to merge it together. So we're going to use the git checkout master. Master's in this common, frequently used workflow is where you merge. So when you're putting things together, it's like your scratch pad for working on different commits. So we're going to switch back to master, but we don't actually want to merge A because A is already an ancestor of both F and G, of both our other branches. So what we want is we want master to point to F or G. So the reset command does that. It relinks the master branch to one of the other commits. So here we could have used any of the other identifiers for the F commit, but we're going to use the bug fix because we know bug fix is pointing to the most recent commit on that branch, and we're going to issue the merge command to merge it with the other branch. So now the bug fix remains the same because bug fix was not the checked out branch. Right, so the bug fix branch identifies the actual bug fix. It should not have anything to do with our wicked branch. The wicked branch should have nothing to do with our bug fix branch because that wasn't their intent. Their intent was to either implement this new feature or to fix a bug. However, the master is what we want to share with the rest of the world. It contains both. And so we merged it together in our Scratchpad branch, the master. So the master advanced. The other two branches did not because they were not the checked out ones. I have a question.
So the reason why you don't just merge in one of them and then merge in the other one is that you lose some of the...
You lose some of the information, right? So if at some point, what's not shown here, but let's say there is another branch, right? Like a branch that identifies a stable tree that might have branched off C or something else. And I want to merge in this bug fix into my other branch. It's much nicer to be able to merge it by its name because I still have it than by going back and finding the commit that actually fixes it, making a patch out of it, and applying it manually. So here I still have a reference to the commits that actually fix the bug, right? Whereas if I merged using the bug fix or the feature branch, I would have had the bug fix on the feature branch or the feature on the bug fix branch, which isn't technically correct. You can do it. Git doesn't prevent you. It's just not the workflow that I'm presenting. So you can use Git in whatever way you want, right? You can not even have any branches and work, in a linear fashion on one branch, or whatever you want. In this particular workflow, we're going to separate the topics on different branches. And I think this is fairly common from what I've seen. Keeps things fairly clean. So we're going to do some, we're going to talk a little bit more about merging. So Git Merge is the command as we've seen for merging, and it takes one or more branches to merge into our current branch. And this can cause conflicts if both branches edit the same content, so modify the same line, for example, in the same file, there's going to be a collision, and that will require user intervention, just like in any other revision control system. And then you will have to go in and fix it. It looks very similar to CVS markup for files. It has a greater than, then equals, and then less than, symbols in the file identifying the conflict points. You can look at the man pages for that. I won't cover it. So we're going to do one more example for merging. So we have a branch pointing to a single commit. Then somebody branches off and they make their own commits. We make our own commits. We're going to check out another branch, and we'll merge them together again, separating the merge branch from the actual topic branches. Then the other two branches still get some more development. The third branch gets some more development. And now we want to merge all three. So we can do this in two steps. But as I mentioned before, Git Merge takes multiple branches as parameters. So we'll switch to our merging branch again, and we'll merge in both of them. So here we're specifying, we're on 3, so we don't have to tell her about 3, but we're specifying 1 and 2 as the two branches we want to merge in, and it just merges all together in one step. Creates a single commit with multiple parent pointers. So not just 2 as we've seen before, because there are more ancestors. So here it's going to have 3 parent pointers pointing to E, G, and F. And this is called an Octopus Merge. Octopus merges happen automatically if you specify more than 2 commits. Rebasing.
Conflict and an octopus merge can be a little confusing.
The comment is that merges and Octopus and Octopus merges can be a little bit confusing. Yes, they can, because they can influence merges across more than just 2 places. I haven't actually ever resolved a merge conflict with an Octopus branch.
You couldn't resolve them, or you've never encountered?
I've never actually used the Octopus branch. For example, take Linux, right? Linux will have, I think they used to be called generals, maybe they're still called generals. So there are people that are responsible for certain components of the Linux kernel. Like there's a SCSI subsystem, there's a SCSI subsystem maintainer. So he's responsible for his portion of the Linux kernel tree. There's another guy that's responsible for, the serial port drivers, right? There's another guy that's responsible for video, for sound, for networking, and so on. So all of these guys maintain their own trees. They all have their own Git repositories. They all take patches that represent changes for that particular portion of the Linux kernel. And then at some point, Linux wants to integrate all this stuff together, or somebody else does it for him, somebody else that sits between Linux and those guys. So they want to actually merge a bunch of trees together at the same time. So they're going to pull changes in from multiple different branches and do an Octopus merge, just because they know that those trees haven't necessarily collided. Because one guy's doing SCSI stuff, separate files from the serial driver stuff, right? So they may not conflict as often. Sometimes they will. All right, so that's rebases. Rebases are slightly similar to branches, to merging, because they accomplish the same feat. They bring together multiple changes from two different branches together into one. But the way it's done is slightly different. It basically moves your new work onto a new baseline, which is the new branch. So we're going to look at an example, and we're going to compare it to a branch. So to a merge. So here we're looking at same tree on the left and the right-hand side. On the left side, we'll look at what happens during a merge. I don't have to go step by step because we've already seen it twice. We have two branches. We do git merge master into test. There's a new commit made. The test branch advances, as we've seen before. In a rebase, oh yeah, that's easy. So in a rebase, what happens is we're on a test branch again, and we're specifying the master branch as the other one that we want to integrate with. The difference is that instead of actually merging and creating a new merge commit, there are two new commits, and actually as many commits will be created as there are on the original branch that we were on that are new, and they're replicated from the original branch. So looking step by step, we're going to take diffs that represent the commits D and E, and there is a lowercase d and a lowercase e in case you can't see inside the triangles, and we're going to apply them individually onto the most recent commits on the master branch, the branch that we're rebasing onto. So the master branch is our new baseline, and we want to take the test branch and put it onto the new baseline and continue development. So in a loop, we're going to take each individual commit starting at the oldest, and we're going to apply it onto the branch that we're specified. So we're going to take the D commit, the D diff rather, and apply it onto the C commit, and that gets us D prime. And then we're going to take the next one, and the E commit has an E patch that generated it. We're going to take that E patch and apply it onto the most recent one on this branch now that we're rebasing onto, and that's the D prime commit, and that gets us E prime. And again, the test pointer has advanced, but now it hasn't actually advanced to a new commit that points to our original work. It now switches over, and the master branch is now an ancestor, or rather the commit that the master branch points to is now an ancestor of the test branch, where it wasn't before. So again, the rebase is an operation that takes your new work and it applies it onto a new baseline that's identified by a parameter. So a place where this might be used is to be able to keep your history clean. This is very similar to the way the subversion works. If you have some work that you haven't committed yet, you can think of this as one of these commits in this graph. When you do a SVN update, it's going to pull all the new commits into your current repository and basically put your work on top of it. It's going to do kind of a merge and put it on top of it. So this happens every time you do an update in a subversion tree. So eventually those two objects off on the right, since they're no longer referenced by a branch or a tag, will actually vanish from the repository. And they can vanish immediately, or there is a feature in Git called Reflog. If you have Reflog enabled, which I think it is enabled by default in the master branch, then it will keep it for 2 weeks. So those commits are not actually lost, and they can be found again through another series of commands. Remotes. So this is I think the biggest chunk of the Git usage section, because it's fairly important, and it's got some new commands that you may not be used to coming from centralized systems. So cloning is an operation that completely replicates a remote repository. So it will initialize a new it will initialize a new repository, the Git directory locally, and it will bring all the changes from a remote server, a remote repository, and populate the local one. And then it will check out the master branch, and it will populate the working tree. It can be told not to if you're not interested in the checkout, if you want to start working on a different branch, but by default it checks out the master. So we can work with different kinds of URLs for cloning. We can work with the local file system, so we can specify another repository on your disk. You just have to have read permissions to it. You don't have to have write permissions. You have to be able to access it. We can go over the HTTP protocol. And last time I checked, HTTP is only used for read operations. So you cannot push to this repository once you've cloned. Of course, you can change what the pointer points to, but by default, you cannot push through HTTP, I think. The comment was that there is no WebDAV. Again, I don't know. Somebody might have written it. I'm not really interested in HTTP servers. They're less efficient for Git than the native Git protocol is. So if you're just interested in the read-only server that's serving out the Git repository, running a Git daemon is far more efficient. And if you look at the man page for Git daemon, it's very well documented on how to run it. And the last one is SSH protocol, which I think you'll probably be using the most. So this allows you to both push and pull, and you're actually authenticating yourself at the server. So when you're pushing to the repository, right, there's a way to prevent you from pushing to particular repositories that you don't have access to. So there are two different forms for the last URL. You can either specify the URL form or the SSH-like form. You can also specify ports for any of these with a colon in the appropriate place where you would expect it. So let's look at some interactions between remotes. So somewhere on the internet, there's a server repo.or.cz, and that's actually the home for the first free hosting service for Git repositories. And that's where the Git project is mirrored. It's originally been hosted on the kernel.org site, just because it's got tremendous bandwidth, and Git was originally written for tracking the Linux kernel. But it's also hosted at repo.or.cz/git.git, I think. So if we want to clone this repository using SSH, we can specify one of the SSH forms and specify the URL of the host and the project. And that's going to create a local repository, as I've mentioned before. So Git actually takes the last word of the URL, in this case project, without the .git extension, and it creates a subdirectory of wherever you happen to currently be. And then inside of that, it creates a .git directory. So the project directory is going to be your new working tree. And the .git directory within that is your repository. So it initializes an empty repository. If you don't like the choice of the project name, then you can specify it with another parameter. So in this case, it's build tree, and it creates a build tree directory instead. And the next phase is the remote is going to prepare a nice new package for you to send over the network. So it's going to count up all the objects that it needs to send you, create a nice little package, and then you're going to receive it over the network. So in this case, I think I was cloning, let's say Git. I think Git's probably about 22 megs. So, I cloned the Git project, so it gives you the counts of how many objects there were, and then the last step. Oh, right. The note here on the left-hand side in the repository, the branch is called master. It's hard to read. The font's a little bit small. So on the left-hand side, it's called master. In our local repository, it's not called master because we have to identify the difference between this master and one that's local, and the one that might have come from another repository. We'll see that later. So in this, what Git does is it puts a slash in between the name for the repository, for the remote, and the branch that it got from the remote. So here it's origin/master. So the master identifies the branch on the remote. The origin is the default name that Git gives as a name for a remote. So because we cloned this remote, it gives it origin, and we're actually going to rename it on this diagram as origin because that's what our local repository knows it as. And you can rename it later if you want. So the last step of the clone is a checkout. Again, by default, you can suppress it. And it's going to take the master branch. It created a local master branch. That's the green trapezoid. And it checks it out into the working tree. And we're good to go. So now we can do development in our own private clone of the remote repository, which we know as origin. We can do some inspection on this. So running git branch-a shows us all the branches that our local repository knows. So it's aware of the local master branch, and it's aware of the origin/master. These colors, again, are taken from the default colors that Git assigns the output if you have the UI option enabled. There's a star next to the branch that head points to. So head is pointing to master because that's the branch that was checked out. Again, this is default when you clone. And we have an origin master, which also points to the same commit because nobody's made any changes. And that's the representation of what we know is on the remote. We can also look at the list of tags, and these are names of certain commits that we're pointing to inside that DAG. So good so far. Somebody else does some committing on the remote, so we have some new commits, G and H, that appeared, and now the master on the origin remote has changed because now it's pointing to H. We don't actually know what H is. The last time we communicated with origin, we got master pointing to F. So until we actually talk to origin again, that's what we know. We think that the origin is still pointing, has a master branch that's pointing to the F commit. But we do a fetch. So a fetch is a command that brings the commits from a remote into the local repository, but does not check anything out. So it doesn't change the working copy. It only fetches. So it only updates it doesn't merge, doesn't do anything. It only updates the remote branch pointers. So the first step, again, very similar to the clone. The remote's going to count all the objects that we don't have yet. The counts there are not representative of the picture. So in my fetch example, there were 236 objects that were new. So every object that I've shown before in previous slides is represented in this count. So this includes blobs, this includes trees, and commit objects. So for a commit, the minimum number of objects that you can get are 3. You're going to get the commit object, you're going to get the top-level tree object, and you're going to get a file object. You can't have a commit that doesn't have any files, I think. And you can't have a tree that doesn't have any blobs, so the minimum is 3. And in this case is 236. So the next step is all this stuff is going to be sent over the network, and that's going to take some time, and then it's going to update the local state of the repository based on what was received. So here we can see that prior to this operation, origin master was pointing to F, the new origin master is now pointing to H, and now we're in sync with the remote. But there are no disk changes. Because git fetch only updates the repository DAG, it doesn't update, and it doesn't update the local branches, it only updates the remote states. And of course, nothing is checked out. So git merge is a command that we can use to merge the origin master. So the animation here was missing, but the master is currently pointing to F. If we do git merge and specify origin master as the reference we want to merge into master, then master is going to advance to H. So H is the what we've merged in basically into our branch. So again, master was pointing to H. We want to merge in the origin master, so we specify that, and this does what's called a fast forward from master to origin master. A fast forward is a merge operation that doesn't actually merge because it already knows what the state of the object would look like after it's done a merge. So if you ask to merge 2 branches and there is no need to merge because that state is already somewhere else in the DAG, then there is no new commit created. It just fast forwards to the new state. And it updates the working tree. I think there's a switch to merge which suppresses the updates, but by default it will check out the changes. So here I've modified the, I think it was fizz, didn't come out correctly on the slides. So there was a file that was modified and it was updated by the merge. So because git fetch and git merge are very frequently tied together, you can just say git pull. And what git pull will do is it will fetch and merge the master branch in this case. So we're going to make some local changes. So we modified the bar and the fizz files, which are in bold in our working tree. And we're going to commit. So that's going to commit. It's going to create a commit ID. It's going to create a new commit called I. And the master branch is going to advance. And now it's pointing to the I commit. So everything we've seen so far before. And now we want to share that particular commit with the rest of the world. So we're going to do a push. Implicitly, the remote that Git pushes to is origin, the name origin. If you specify a different name after push, then it's going to push to a different remote that you have a relationship with, which we'll see in a minute. And that's going to basically advance the master branch on the remote if you have write permissions to the remote tree. So very similar output. It's counting object. It's sending them over the pipe. It's updating the remote to the new branch. And also, Git notices that the remote branch master, the origins master, is now pointing to the I commit. So it will also update the state locally because that's the operation that we've made. So now our local master and the remote master are the same commit.
What if somebody's made another modification to origin before you did a push?
Then it's going to complain, and you will have to pull or fetch and merge, and then push, just like in Subversion if there is a conflict. Except for in Subversion if there's a conflict in another file, because Subversion commits aren't really atomic, it will not complain. But Git will always complain if there is an outstanding commit on the remote. It will tell you, basically, no merging can happen on the remote. The remote never merges. The remote never creates new commits. Only the local side can create new commits and merge. So you have to get those changes to your local repository, make the merge, resolve any conflicts, and then push that to the remote.
So is that the equivalent of the remote doing a fast forward then?
This is a remote doing a fast forward. The remote can only do a fast forward because it can't create new commits. Well, it can probably create new commits with hooks. I haven't mentioned hooks, but inside the Git directory, there's a hooks directory with a bunch of shell scripts that get executed at different stages of the Git processing, and so I believe that it might be possible to create new commits and do even conflict resolution inside those, but I'm not sure. All right, so meanwhile, somewhere else on the internet, there is another server that's interested in this work, and this is probably a good time for a break. So I'll take a 5-minute break, and then we'll resume after that. Okay. So where we left off is somebody else on the internet was interested in this particular repository, so they're going to go through the same kind of process. They're going to clone it. So Fred clones the project, and he gets the DAG in his repository. He gets his own working copy, so we think. We don't know because we're not on the system. And he makes some changes, so there's a new J commit in his tree. However, Fred doesn't have push permissions to our repository. Let's say he cloned using the HTTP protocol. And so he sends us an email, and let's say we're the maintainers of this project, so or one of the developers with push permissions. So he's going to ask us to pull from his repository. So he's given us the URL, and we're going to take that URL from the email, and we're going to add a remote. So Git Remote is the way you interface with the way that Git tracks remotes, and we're going to add a Fred remote. So Fred here is the nickname. We're going to be calling this remote as Fred. We can call it as by anything we want. Just typing in the URL every time is not very convenient, so it's got to be something else. And so we'll just rename that repository on the right-hand side as Fred. And we'll fetch Fred's changes. So we're going to grab all of Fred's changes and bring them into our repository. So as we've seen it before, that's going to bring all the changes over. It's not going to touch the origin master branch, which is the red trapezoid on the left side in the local repository rectangle, but it's going to bring a new remote branch into our repository called Fred/master, and it's called Fred master because we've given the remote that Fred has published for us the nickname Fred. So here we have Fred master pointing to the J commit, which is the one that Fred created. And because J was based on I, there's obviously a parent pointer to I in our tree. So we can do Git Log on Fred master to look at the changes that Fred has made before we actually commit to including those changes into our actual origin repository, our origin remote. We can do git log Fred master and then nothing on master. So here's a way to show all commits which are on the remote branch but are not on the local branch. So this is just going to show us the change that that Fred made, which is J. We can also look at the patch that's included by that commit. So the -p option will show the diff. It's kind of like show, but it can show multiple patches. So if Fred made multiple commits, it would show us a different patch for every commit that he made, and then preceding every patch in the output will be the commit header telling you about the SHA-1, the committer name, and the date, and so on, the message. However, a better way of inspecting Fred's changes would be actually to get it into a working tree. So we're going to create, with the checkout command, we're going to create and switch to a new branch. We're going to create a local branch called fredfix, and it's going to be pointing to the state of Fred master. So the remote Fred has a master branch. That's the one we want to check out. So now we have a new branch in our tree. It's pointing to the J commit. It's called fredfix. It doesn't have to have the same name as master on Fred's repository, and it's tracking the Fred master branch, or it's pointing to the commit that the Fred master branch is pointing to. Once we're happy with what we saw, we can merge it back into our master. So we're going to do git checkout master to switch to the master branch. And then we're going to merge in Fred's fixed branch. We can say here git merge fredfix, or we can say git merge fred/master. They're basically equivalent because they point to the same commit. What we're actually merging is the commit. Using the branch name is just icing.
So you could actually use git merge and then the
Full SHA-1 if you want.
the full SHA-1.
Yeah, you're merging commits, not branches, really. Here we can drop the fredfix branch because we no longer need it. So git branch -d removes that from our tree. And then we can push this to the origin remote with git push, and it's going to bring the new commits that were generated by all this work to the origin master, and then subsequently Fred can fetch the origin remote and get all these changes in his repository and see that his change actually made it to origin. Or he can just dispose of his repository and never look at it again. So because the origin master branch was advanced to L, again, Git notices that and updates the states locally. So the origin master branch, which is the trapezoid on the left, is now pointing to L. Is there a question?
Yeah, if Fred has made multiple changes, should I use also merge or rebase?
You can use whichever one you want. What rebase does is it allows you to clean up the history, make it more linear, so you don't have a lot of branches when you're visualizing it. It's also useful because rebase has an interactive mode which allows you to squash commits. So if Fred has developed a particular change and he uses micro commits to the extreme, he has a commit for every line of code that he changes, and you don't like that in your repository. You like to have big commits that identify features. You can squash all that together using an interactive rebase and then bring it into your repository. Or you can use something called a squash merge, which does something similar. Anyways, you can use rebase to clean up your repository. That's where I want to get to. The only comment I'll make since you're asking a rebase question is that it is difficult for other people to work with your remote if you push your squashed changes into the repository very often. So because a rebase, as we saw, creates new commits that have new SHA-1 sums and are not representative or are not linked in any way to the other commits that were used before the rebase. So we had on the left-hand side, we had 2 commits, and on the right-hand side, we had 2 commits. Well, Fred has the commits on the right-hand side because he cloned the repository before you rebased. Then you rebase the changes, right? So when he pulls the new commits to his tree, he actually has to do a merge. And that's difficult because that merge could introduce conflicts. And now he's merging code that he had nothing to do with. right? So pushing rebase changes to a remote repository is often frowned upon. You should do your rebase before you push to origin. So in this case, if you did a rebase instead of a merge, that's fine because you haven't pushed those changes to origin before. But what's frowned upon is pushing commits to a remote, then doing a rebase to clean up your tree, and then pushing again because you're forcing the state of the remote to change. But somebody else could have come along in between those two pushes from your repository, grabbed your tree, and now they're forced to do a merge. And again, this could be confusing. They have to do extra work, and they just want to get your commits. So that completes the remote section. And I'll show you two GUI tools. There's Git K, which is a way to visualize the revision tree. And there's Git Gui, which basically trivializes the staging process and the commit process, the branching process, and the remote tracking process. It's for people that are more comfortable with tools like Tortoise SVN and Tortoise CVS, or the Eclipse plugin for either one of those two revision control systems. Mentioning Eclipse, I don't know if you are using Eclipse, but there's a eGit fork of Git, which is a pure Java implementation of Git. I have absolutely no idea how far along it is for features, but it's a way to integrate Git natively into Eclipse if that's what you're into. So anyways, Git GUI, just a GUI that trivializes some of the simple operations. For more complicated things, you're still forced to go down to the command line, but for everyday use, I think Git GUI is probably okay. So Git K. Git K looks like this, and because the fonts can't possibly come out okay after they're scaled, I'll show you Git case in another window. So this is Git K running on the Linux kernel, and few things to identify here. The branches are green boxes. The one with the bold lettering is the one that's currently checked out, so the one that head points to. Here we have a remote branch, which is prefixed by a red background box that has the name of the remote, and then the name of that branch on the remote. So I cloned the Linux kernel, and for me, this is the master branch. For Linus's remote, this is also the master branch, and my repository knows Linus's tree as origin. Here's what a tag looks like. This box here. Below the list of revisions, we have a short description about what this commit is all about. Because this commit here, the one that's yellow, has 2 lines coming out of it. We know it's a merge. Here in the parent list, we can see that it's got 2 parents. The red one is this red line here, and the blue one is this blue one here. And it doesn't have any actual changes because it's a merge, right? So it may not introduce any merges, any changes on its own. But if we walk down to the next revision, we can actually see some data here. So there's a long description here of the commit. Usually in the kernel, the closer you are to a release date, the longer the commit descriptions are because there are fewer and they get more scrutiny if they have short descriptions. Also, the bugs that are getting fixed are far more obscure, so they need to be described. Anyways, here's a list of files that are modified in this particular commit. So we can look at that particular change. Here's a 1-line change and a 30-line or 40-line description of what actually happened there. I don't think there'll be too many commits here at the top that actually have multiple files changed out here too, right? So if you click on the first one, it shows you the first diff, and it's just scroll downs, right? So I can scroll down manually or just click on it and it shows you the changes. So let's see if we can find some Octopus merges.
So those are the commit messages?
The thing at the top, this is the header, the commit header. So this identifies the metadata about the commit. So here's the author, here's the committer. All right, so here's how it differs. The author is the person that wrote the patch. However, a person may have acquired this patch through an email, in which case the person that wrote the patch is not the committer. They did not commit this to a repository. If this person, David, committed this to a Git repository, and then subsequently Linus merged it into his repository, the committer of the commit is still David. But if Git acquired it through some other means, through a patch or through a rebase, the committer might have modified that commit, right? Because the SHA-1 will not match what the remote person had. So the committer is in charge of committing it to the repository. He's the person that finally actually adds it to the repository. And it could be the same person or it could be a different person.
I just meant the paragraphs there.
Yeah, well, so yeah, I'm gonna talk about it.
Is it common for the Linux kernel to have huge messages like that? Usually in other revision control systems, you just put a one-liner.
You can put a one-liner.
But
Yeah.
But,
It is good form to describe your commit.
oh, sure, but
Yeah.
this is.
There's a lot of review on Linux kernel.
As opposed to a previous company where I worked, where before one of the key developers went on vacation, he would just throw a one-liner. If he actually wrote any comment there, he would actually throw a one-liner into the commit message saying, check in before vacation.
Nice. Or changed some code.
Sometimes you just put a ticket number there, right?
Sure. Yeah. Okay. So, anyways, you can make it as long as you want. There is a convention in the Linux kernel to add signed off lines, and actually Git has support for this. When you make a commit and you are or you want to sign off on a particular commit, you will add this sign off line, which basically identifies that you approve this change. So here are some people that are high up in the development in the tree of people that develop the Linux kernel, and they are basically happy with this particular change. But yep.
Question about the sign-offs. Since you're changing the commit message, wouldn't that change the SHA-1?
It would. Yep.
So how do people sign off on the same commit and have more than one people?
Do
you need to merge your sign-offs.
Okay, so let's say that you've made a change, okay, and you have a tree that you want me to pull. So you send me an email, please pull from me, and I will pull from you. And then I'm going to look at what your tree looks like, and I will probably cherry pick that commit, or I will just amend your commit with my sign-off message. It will no longer be the same as your commit. So you will, when you get my tree again, you will actually have to throw away your change because it's already on the tree in a different instance.
That's why
And
this
this,
is the committer in that one.
because probably, yes. Yeah. Some of the sign-offs happen just because the patches come from an email. A lot of the development on Linux is still happening basically by developers cloning the Git repository or just grabbing a tarball, Linux tarball, creating a patch, and then sending it off to the mailing list. And then somebody will pick it up, like one of Linux's subsystem maintainers, and they will include it in their tree. They'll sign off on it. That will then get sucked into somebody else's tree. That person likes it. They'll sign off on it. And then eventually Linux will pull it in. And that patch may no longer look like anything like the original change. You'll get the gist, right? The patch might have shifted up and down because other code was merged in at the same time above it or below it. And people might have signed off on it, so that creates a new commit header. People may actually modify the commit header. The patch may change. So it will probably keep the author, but the committer might have changed several times by the time it reaches the upstream repository.
But that's the thing that's special with the Linux kernel, right? Like if you're using it in a company,
That will probably not happen.
the
Yes,
author
that's
and
right.
committer match.
Yeah, because in the company nobody reviews your code, right?
Nobody signs off.
Nobody cares about what gets in. I was trying to find some kind of commit that has multiple parents, and I can't really see any. But you can see there's lots of branch. Oh, there's some. Oh, so here actually, this is the opposite of what an Octopus commit would look like. So here somebody took a merge, and then merged from another tree, and then merged from another tree, and then merged from another tree, and so on, right? So all of these were individual subsystems that were merged into one tree.
Is that smarter to do than Octopus Merge?
It is smarter if you have conflicts.
It's easier to...
That person might have ran an Octopus merge, got 1,000 confusing conflicts, decided, oh, this is not the way I want to do it, and do it manually, and there probably was only one conflict that they had to resolve manually, or maybe two, right? So was that an Octopus one? Anyways, Octopus merges exist, but they may not be very frequent.
There's very few people that would have done an Octopus Merge.
That's right, because they may not know about it. Okay, so
Say you could search for the people who are most likely to have done it.
Right. So there's a way to filter. I mentioned before in Git Log that you can filter how you're looking at the information. So this is the view. So I actually specified --all and 10,000 on the command line. Remember the dash number form means that I only want to see the most recent 10,000 commits because I don't want to spend 5 minutes waiting for the history to load up since the beginning of time. But I can also specify committer equals Linus, and I don't know if that's going to actually work. There may not actually, no, I don't know how that works. Yeah, that will do. We probably have to spell it correctly for it to work. So this is going to include the last 10,000 commits that Linus has been the committer on. So it's probably going to create a lot of merge. It's going to include a lot of merge commits because Linus doesn't do all the development, as he claims in many interviews. He is mostly interested in, well, I don't know if interested, but he is forced to be the guy at the top that just basically merges.
Does he tend to do multiple merges together or merge at a time?
It seems to look, it would seem that he merges a few trees at a time, one individual tree at a time. It's, yeah, I don't know, maybe it require, oh, it's not Linus, it's Torvalds, that's why. Does anybody know how to spell Torvalds? Actually, here. There we go. It's much easier to spell. There's got to be an Alan, right? Oh, there's a David, so I'll do David. I'm sure it works. Come on.
You're saying about Git being fast?
Sorry? Well, it's David here, and I think it just does a sub string match. Oh, he's not the committer. All right. Okay. Anyways, so I think it works. Oh, there we go. All right, we found. All right. So here we found something that had something that had a David in the committer field. So the reason why I didn't match the first few because the David was actually the author, not the committer. So it had to search down to this guy that is the libcrypto maintainer, maybe that actually merged this commit. So you can see that these are disjoint, right? Because it's not necessarily true that all the commits by this guy are sequential, right? So he works in spurts and gets commits included within certain ranges, but he doesn't have all the commits, right? So these will be discontinuous blocks, and it still finds all of the tags and all the branches that these things point to, but they're not necessarily contiguous. You can also specify branches or tags here. So let's say we were interested in a similar kind of query, but this time I'll limit it a little bit more at version 2.6.16. And I actually won't search all the branches because I know it's only on that one. So it's going to pull in the tag for the 2.6.16 release, and then we have the 100 or so commits below that. And here we can see the last RC before that. So all of the switches that I've been actually adding into here are the same kind of switches that you would add to Git Log. So Git Log, right, shows you that, and Git Log -2 will show you the last two. Pretty one line. We'll show you a commit per line. I actually have a Git alias for this. That's why I don't know whether it's one line or -1 line, because I would do this very often. So if I want to review the last 100 commits, I don't want to see the whole block. I just want to see a short little description, the commit ID, and the first line of the commit. I think I also have an rlog. which will also include the date and the name of the committer, as well as the description. But there's a tool called TIG, Git backwards, which is a curses interface for Git. So, right, you can scroll through this. And the nice thing about TIG is it also pulls in branch names up here. So I know that this particular commit is origin master, and it's origin head, and it's master. And if I click on that one, it brings up the commit message, and I'm sure there's a way to look at patches, but I don't have much experience with it. So that's Git K. So the other one is Git Gui, and it looks like that. And if we run it on the kernel tree, this is what it looks like. So here on the left-hand side, the output on the left-hand side is actually the same as Git Status. So it's going to show me that this particular file was modified, is untracked. So I haven't added this file to the repository yet. If I edit the file, like let's say remove that line, then Git Status is going to show me that 2 changes were made. So it's going to show me that I have a change that's not something that's been changed but has not been updated yet. It hasn't been staged. So I need to run git add to add this file that has been modified to the index in order to stage it. And it tells me that this file is untracked. So now if I do git add, as it tells me, then it hasn't made a commit, right? Because I just added the file to the index. So now instead of being a changed but not updated, it's changed and it's to be committed. So it's telling me I can do git reset head file to unstage it. So Git Status again shows me that the make file, again, notice the color difference. If it's modified, it's staged, it's green. If it's not staged, it's red. And that's the make file. So we can do the same thing with Git Gui. Of course, I don't use this very often, so I don't know how to update my repository. If you see update here, let me know. Maybe there's a rescan. Where? Rescan F5. Of course, F5 makes sense. All right, so we have a file with a nice little icon that is being tracked, and it has a change, but it hasn't been committed yet. To be committed, it has to be staged down here. So we can see that there's a change. Oh, this is a cool feature. So I gotta go back and make another change. Because all right, so I'm going to remove another line. Actually, I'll add a line. Make it more interesting. So I'll rescan. All right, so now we can see that there are 2 hunks in this file. Hunks are names that are given to sections of a patch file. And if you ever saw a patch or a diff output, there's a block that starts with @@. That basically means that this is a hunk. This is the start of a hunk. So in our first hunk of the diff, we have a line that was removed, and it was replaced with an empty line. And here we have a line that was added. Now, this change doesn't make any sense. Why would I ever commit that to the repository? But this one, that's cool, so I'm going to include that. So you can either get the whole file to be staged, or you can stage a hunk for a commit. So what this is going to do is it's going to split the file, and it's actually only going to put this part in the index, and it's not going to put this part in the index. So here you have a list of the unstaged changes, which includes our stupid edit. And it's going to, and here is the staged version of the make file, which includes the diff that we did want to commit. So here we're going to put our commit message, and we can sign off on it, which just adds the sign off. Cool. I haven't seen that. All right. Probably because I'm not running GNOME, right? So so here's the commit message. And that's the sign-off string that I've added. And then when I commit, it's going to create a new commit. So I'll do that. And now all the information about the staging is gone. If I go back here I can see that my makefile is not staged. Git diff will show me that I have my my edit that I didn't want to include. That's still outstanding. Git show. Git show is going to show me the last commit that I've made. So here's my commit message, which is good enough to be used at a corporate environment. Here's the commit that I made that was actually included. If I'm not happy with this commit, remember I can't modify things, but I can replace them. So if I'm not happy with that actual commit and I want to change it, I can do an amend operation. What amend does is it brings you into an editor and allows you to recommit what you've committed. So you can modify the message. So here I'm going to change that into removed line from make file. And we can see that that the commit was actually changed. And if we took notice, the SHA-1 is different, right? So if we scroll, I nuked it. So I'll show you Git Reflog. So Git Reflog shows you the history of a branch. So it doesn't show you the commit history, but it shows you the modifications we've made to a symbolic name. So it remembers where the master branch was pointing before I made this change. So here we have the list of the SHA-1 IDs, and they're short form because otherwise stuff wouldn't fit. So we can see that matches the first, I think, 6, 7 characters of the full SHA-1. But we can see our bad commit, right? So we can actually look at this, even though it's no longer in history. If we look at Git K, we can see that I have a local outstanding uncommitted change, which is that one, right? Which I didn't want to commit. There's the commit that I've made, which has the proper commit message, and then there's Linus's last commit, which is when I pulled. But there's no mention of that gobbledygook that I put into the first commit message. However, since I have the commit here in reflog of the commit that was actually dropped, I can do this and look at it, right? So if you visualize the DAG at this point, I'm looking at a commit that doesn't have a branch pointing to it. It's still floating off in the repository somewhere, but no, there is nothing pointing to it. So the next time that Git behind the scenes does a cleanup, well, behind the scenes, you actually have to issue a Git command, which checks the state of the repository and sees, oh, you have too many loose objects hanging around, and does a cleanup. Until that happens, that object will exist, so I can always reference it. And reflog is a way to access that if you don't know the SHA-1. Basically, you can find it. So I can also use the cardinal representation, which is one back from the current state of head. So this it's not the same as saying head ~1, which would be one commit prior to whatever head points to, but it's one state of head back in history. So again, we have the commit that we didn't like the message of. All right, so that's, I think I started this tangent with committing or staging hunks, right? So this is the staging of hunks.
Can you delete that unwanted modification in this?
So this one, this change?
If you can sort of cherry pick ones to be able to stage, I would have thought that you should be able to just...
Sorry, but it's not staged, so I can't unstage it, right?
Okay, so you can't, okay.
No, there's a way. I can do it from the command line, so I figure you can do it here as also.
Well, I just wondered if you could actually delete a particular patch.
Is there a revert?
Yeah, right there. Halfway down.
Revert. All right, so yes. And it's gone.
Okay, but that deletes, basically undoes all of the changes to it rather than just undoing one particular
Right,
patch.
so you want to be able to undo a patch,
Yeah.
or undo a hunk.
Undo a hunk, yeah.
I guess the way to do it would be No, I don't think there is a way through this to do it. No.
So you can cherry pick hunks, but you can't
Well,
nuke
you
in.
could.
Well, don't say cherry
choose the
pick
hunks you wanted
because-
And then toss the rest, right?
You can't cherry pick hunks because cherry picking deals with commits. It's just in the Git terminology. But you can stage hunks that you like.
Okay.
Stage the hunks that you want to commit. Complete the commit. And then
Actually, you don't even have to commit. So you stage the hunks you like. Now they're in the index. Then you do a reset of your working tree, and then you take the index and you check it out with the git checkout command. But now we're getting into the plumbing.
Sure, but I was thinking if you've got a file that's got, I don't know, 3 dozen hunks in it that are good and 2 that suck.
And do you want to commit the good hunks right away or
And
later?
you want to commit basically the whole thing except for the 2 bad hunks. So
Oh, so you can. Oh, okay. So you can stage the whole thing. Yeah. So you can stage the whole thing and unstage one hunk. I thought you wanted to remove it from the working file. Okay. So yes, you can stage the whole file and then you can unstage one hunk. So the way to do this from the command line is git add -i. Unfortunately, I have to have a change. So 1, 2, 3. So what git add -i presents me with is a text line interface, kind of like mudding in the good old days. So it's going to show me the list of files that have unstaged or staged commits, and it's going to tell me that there are 5 lines that are modified, or 5 lines in the diff that need some attention, and they're in the makefile. So if I do the p command for patch, it's going to ask me which files. Then I'm going to say the first one. And then it's going to show me the hunks one by one, and I have some options to include or not. So here are the options that you have at every individual hunk. So we're going to stage this hunk, or
you were saying you could stage the whole thing and then just...
all right. So let's do that. So I controlled C.
One that you don't like.
So one way to stage a complete file is to do git add makefile. And I'll do git add -i, and I'll go into the patch mode again. Oh, you can't do it with this. All right, so there you go. You need to use the GUI. So if I go here, I have a bunch of the 3 hunks that I'm interested in, and this one, and we'll unstage it. All right. So now we have the one that we didn't like, and we had the 2 that were the majority of the hunks we wanted to include. All right. So checkout -f blows away all the changes in the tree. And git reset -hard also does that to the index. So now we have no changes, but I've actually made a commit that's going to make it hard to interact with this tree later on. So I'm going to git not just reset hard into head, but head till the 1. So I'm going to go back to the previous commit, which is the commit before I made any edits. So now, yeah, right. That takes a while. So now I have 100 commits, and here's the top one because I've removed the one I had before. If I go into Reflog, then I can see both my bad commit message and my good commit message, and it even tells me, I'm not really sure how it knows, but it kept track, it knows that I've amended it, so that commit came from this one. Or sorry, this commit came from this one being amended, and then I reverted back to this one. I think I had the question?
Yeah, I have a problem because I had some confidential data in a file, and then I committed it, and then I pushed it to the remote. After that, I figured out, oh, I need to delete it from the file again, and then committed the changes. But you can still see the confidential data when you do Git Log, and you see the difference. So is there a way to remove?
Okay, so in order to change history, you need a conspiracy. Everybody has to be involved, right? Because if I cloned your repository, before you use this command to filter the branch, then I still have your private data, right? I can keep it forever, store it on a DVD, sell it in 10 years or whatever. Well, I don't know if DVDs last for 10 years, but whatever the limit is. So you need a conspiracy. So private data, probably you're in a company, right? That's why you care. You have something that gets the company in trouble or releases IP or whatever. So you can have a conspiracy because you're a cohort of people that can get together and do this removal of the private data, right? So you can decide that you all want to reset onto this new tree that doesn't have that private data. So there is a tool called Git Filter Branch, which basically goes through all the commits and it applies a script which allows you to rewrite any commit based on a pattern. So there is a way of removing files, there is a way of filtering out commits, there is a way of filtering out diffs, and this man page tells you and gives you examples of how particular tasks would be done. All right, so like I said, there's tons of information in these man pages now, and lots of examples, which is one of the cool things that happened in the last year or so of Git development, is there's been a lot of pressure of making very good documentation. So basically everybody in the company would have to be in on it and told to, after this step is completed, to now start using the new tree and blow away their old one.